Hi, my name is Leonardo Cardoso, and today we'll be doing the tutorial Fit Cortex Lab with GNU Radio using Docker. In this tutorial, we'll learn how to use Docker to play around with GNU Radio in your own computers, but we'll also learn how to export everything into the Fit Cortex Lab testbed and use the nodes that we have in there to play around, try things, and learn how to use GNU Radio in general. I am an associate professor at INSA de Lyon, and I'm also a researcher at INRIA. And I am one of the lead researchers of the Fit Cortex Lab testbed here in Lyon. So before we start, let's go over some of the steps that you should have taken before coming to this tutorial. First, you need to have a Docker Hub account. You need to have also the Docker app installed in your computer. Then you will need a compatible X server installed, be it in Linux, Windows, or in macOS. You will also need a compatible browser for BOKU Gui. And you need also to be sure that Docker works correctly in your computer. These are the required steps such that we can start working with this tutorial. Now, let's go over the first steps that are required in order for us to start working with this tutorial. These steps will be running in the background while we start the presentation, and then when we finish the first part of the presentation, they should be completed already in your computer. Basically, what we'll do is we will create a temporary folder where we will do all of the tutorial in, and then we will do a Docker pull of this Docker image that is stated here in your screen. So in order to do that, we'll have to open a terminal like this one right here. We will have to type in the commands that we have just seen in the screen. First one being this one to create a temporary folder. Then we get inside of the temporary folder, and then we will do a Docker pull of the image we'll be using today. Like this. While this command runs in the background, we will continue with our presentation in order for us to be ready to start doing the tutorial. Now let's move on to the motivations and the introduction for this tutorial. The main motivation is a follow-up to a previous tutorial that we did in 2018 with respect to Fit Cortex Lab. In that tutorial, we showed how to use Fit Cortex Lab to play around with GNU Radio, but things have changed since. Now, Fit Cortex Lab has a new experiment paradigm which is fully based on Docker. And this new paradigm has few advantages over the last one. Now, Docker experiments allow for 100% reproducible and repeatable tests. We have full access to the nodes, meaning that we can connect to the nodes and do whatever we want in the nodes. It is now easier to develop for Fit Cortex Lab on any machine, meaning that you can use your current machine without needing to change or to reinstall anything, and you can develop on GNU Radio for the target of Fit Cortex Lab. There is now a new user management system and web app which allows you to change your user configurations. And now the robots are operational, meaning that you can use them to do fully mobile experiments. In the next months, we're going to install 5 new USRPs of the kind N2444R, which are X310 compatible with dual synchronized SBX and 160 megahertz of band. And we're going to have also a new reservation management system. So why use Fit Cortex Lab? Well, Fit Cortex Lab is a useful tool that will allow you to do many things, and among them is to learn, practice, and teach GNU Radio. It is actually a testbed that contains actual hardware, so you don't need to have hardware at home to test your GNU Radio systems. It is also repeatable, meaning that you can use Fit Cortex Lab to do automated testing and automated running of tests of any kind of system that you're trying to develop. Since the Fit Cortex Lab room is isolated from the outside world, it means that every scientific experiment running in the Fit Cortex Lab is reproducible. If you run an experiment today, you will have the same results if you run tomorrow, because the propagation environment is constant and we are protected from outside interference. Due to the electromagnetic shielding of the room, we are also not only protected from outside interference, but also we are protected from creating interference into the outside world, meaning that we can test on any frequency and at any power level that we want, of course, limited to what hardware supports. There are many nodes inside of the Fit Cortex Lab experimentation room, meaning that we can also test with large-scale networks. And we also have a big GPU server that will allow you to test either CUDA-based GNU Radio or to do any deep learning kind of experiment that you want with it. So what are we going to learn today? We're going to learn how to use GNU Radio on your own machine with a Docker image. This is a plus. I haven't seen any tutorials out there that teach you to do GNU Radio on your own machine, whatever it is, Windows, Linux, or Mac OS, from a Docker image. We will also be developing in GNU Radio in a Fit Cortex Lab friendly way. You will see that this is needed in order to use Fit Cortex Lab to run your GNU Radio experiments. We will be doing the basic Fit Cortex Lab usage, which is basically connect to Fit Cortex Lab, reserve a slot, time slot, and submit tasks. We will be running a test scenario in Fit Cortex Lab, and we will be using BOKU Gui to observe and interact with the running Fit Cortex Lab GNU Radio experiments in real time. Now let's talk about Fit Cortex Lab. So what is Fit Cortex Lab? Fit Cortex Lab stands for Future Internet of Things, Cognitive Radio Testbed and Experimentation Lab. It is a state-of-the-art facility that allows experimentation for radio at a large scale. It also allows for remote experiments, meaning that anyone in the world can access to the Fit Cortex Lab testbed through the internet and can run their own experiments. It is also a shielded and semi-anechoized experimentation room with 60 plus dBs of isolation throughout the frequency range that are used by the SDRs inside of the room. The shielding also creates a stable propagation environment that is conducing to reproducible experiments, as we said before. And most importantly, it is free, as in beer, to use. Here we have a list of equipment that we can use with Fit Cortex Lab. We have a total of 38 nodes, a node being a Linux PC plus an SDR, and the SDRs comes in three kinds. A CISO SDR, which is a National Instruments N2932 USRP, and we have two MIMO ones, which are coming from NewTek. These are the Pico SDRs, MIMO 22 and MIMO 44. All of them are compatible with GNU Radio. We also have high-end measurement and signal generation equipment that can be used on the request. We also have support equipment, this timing, for example, like the octoclock, networking equipment, and so on. We have robots that can be used for mobility. And we have a Sigfox base station. Finally, one very important piece of equipment for the Fit Cortex Lab testbed is our GPU server, which can be accessible by the users and by the nodes. We have two high-end graphic cards that can be used for deep learning and also for CUDA inside of a Dell PowerEdge 640 computer. And there are many applications that can be coming from the usage of this GPU server, which can be Cloud Run, centralized systems with remote radio heads, or intelligent radio, among others. This is what the Fit Cortex Lab testbed looks like from the inside. You can see the robots here and the equipment installed on the ceiling. You can also see the blue absorbers that are helping to manage the propagation profile of the Fit Cortex Lab experimentation room. The experimentation room is also one of the very important aspects of Fit Cortex Lab. And it looks roughly like this. We have a room which is completely shielded with a metallic tissue that's shown here in gray. Some of the sides and the ceiling of the room are covered with absorbers, as you saw in the picture. And then we have the nodes which are attached to the ceiling connected to a metallic grid. The nodes are comprised of a computer and an SDR, and everything is connected through a networking interface through a big rack of switches, which is connected to the outside world with a fiber optic cable onto our server rack. And then the server rack can be accessed by our users through the internet. This is how the SDRs are distributed inside of the Fit Cortex Lab experimentation room. You can see here the USRPs in gray and the Pico SDRs in blue, and the position marked by the crosses are the actual placements of the antennas for each one of these nodes. The antennas are distributed with a distance among them of 180 centimeters. To help with experimenting with Cortex Lab, we have done some USRP TX and RX characterization, where we have measured the actual transmit power with respect to the gains which are configured for the USRPs, both for transmit, that is the graph on the left, and receive, which is on the graph on the right. And we also measured the path loss from one node to all receive nodes. And all of this information can be found on our paper, which was published in the CrownCom 2017 in Lisbon, whose reference is shown here in this slide. If you're interested in planning your experiment by knowing the actual transmit powers and also the path loss, I recommend you take a look in this paper. In a nutshell, using Cortex Lab means using these two tools, the OAR suite of tools and Minus, both of them to reserve and to control your experiments. The experiments are coded in GNU Radio, but are not limited to that. And the results are automatically copied into the user home folder, where they can be copied onto your own computer and examined. With respect to analyzing a running experiment, there are two tools available. The first one is the FFT Web, which allows you to export any graph from your experiment onto a web browser, and also the BOKU Gui, which it not only allows you to export any graphs onto any web browser, but also allows you to control the running experiment. So as I said, there are two ways to use Cortex Lab. The first way is what we call the legacy method, in which a user connects to an SSH frontend, creates a Minus task, submits the Minus task, and then Minus takes care of deploying the task and then running the experiment on the nodes by itself. Results and debug messages are then brought back to the SSH frontend, where they can be analyzed. In this method, the user does not have control of what is running in the nodes in real time. So the user needs to prepare everything beforehand. The second method is the Docker method. So in this method, the user also connects to the SSH frontend and then submits a task. But unlike the legacy method, the Minus server is actually deploying a Docker container on the nodes. And then after that, the user can connect through SSH all the way from his home computer to each one of the nodes. The user can also export the X window display, so he can have a running GUI on his own computer but also the user can interact with the running experiments in the Docker containers using BOKU Gui. Now let's do a very brief introduction to Docker. A thorough introduction to Docker is out of the scope of this tutorial, so I'm going to go very briefly into the aspects of Docker which are important to us. What is Docker? Docker is something that runs on your computer like a virtual machine, and it's used to do fast deployment of service products. Such service products are actually living inside of things which are called containers. The containers are running on your computer in a fully isolated way, which are isolated from your host OS, but also isolated from other running Docker containers. A container is actually a bundle of software which contains its own dependencies. And that is very useful because it makes it independent from the host OS and software versions, which means that we can have a completely different version of running software and of libraries from that of the host machine. And this is very useful to ensure that the containers can run in any computer. So why use Docker in Cortex Lab? Well, we had several problems with our legacy system that we are trying to address with Docker. One of the big problems that we had is that every time GNU Radio was updated, all the prior experiments were broken, and this needed constant updates from the user side. For example, going from GNU Radio 3.6 to 3.7 broke many of the experiments that were currently running on Cortex Lab. And in that way, the users needed to update their experiments from 3.6 to 3.7. Now we're going from 3.7 to 3.8 and actually from 3.8 to 3.9, and we want to be able that an experiment that was running in a certain version of GNU Radio is still able to run in that version of GNU Radio, whatever the node OS is at the moment. We also had some other limitations with the legacy method. The most requested feature for Cortex Lab was direct access to the nodes. Those were impossible with the legacy method. Also, it was very hard to maintain and to deploy GNU Radio systems with out-of-tree libraries or any other kind of library that could be used by your own GNU Radio experiment. And finally, it was very hard to make BOKU Gui work with the legacy method, as you will see with the Docker method. One other advantage of using Docker is that you will have the exact same version of GNU Radio in your own machine as the one which will be running in Cortex Lab, meaning that there aren't going to be any surprises when you export your GNU Radio flow graph to Cortex Lab. Finally, if you do not like our version of the toolchain that is running in Cortex Lab, you can actually make your own, getting our Docker file and then going from there on and then installing your own versions of software, libraries, anything you want to do. And most importantly, you can run GNU Radio on any computer very easily with Docker. That was actually very hard before. You needed to install GNU Radio natively on the computer, and you will always run in trouble doing that. It was notably very hard to install GNU Radio in macOS and in Windows, and now with Docker you can have a full running GNU Radio version in any computer that supports Docker. And that is actually very easy, as we'll see. Now let's talk briefly about BOKU Gui. BOKU Gui is an alternative web graphical user interface for GNU Radio, just like the Qt one, for example. And the idea of BOKU Gui is that you can have a graphical user interface which is exported to a web browser through a network connection. This is very useful when, for example, you're running your GNU Radio flow graph on a computer which is not the same one as the one you are accessing internet from. This means that you can point your browser to a certain address in a certain port and then have a graphical user interface that can be used to control and to watch your GNU Radio flow graph. BOKU Gui provides instruments, for example, like an oscilloscope, like a spectrum analyzer, just like the Qt version, and also provides graphical user interface controls that will enable you to change the state of your flow graph in real time. It is relatively bandwidth friendly when compared to other methods of controlling GNU Radio at a distance. The most notable one being exporting your X window into an X server display. And BOKU Gui does a very good job at creating an exported graphical user interface given the limitations of your bandwidth. One very important thing is that BOKU Gui does not come in the vanilla version of GNU Radio, so you have to install it by hand afterward. And sometimes the installation is very complicated, so it's actually very useful to have a Docker image with BOKU Gui already installed as the one we're going to use in this tutorial. So now we're going to start with the part of the tutorial where we do the local preparation of your computer to be able to start developing for Fit Cortex Lab. So what we're going to do is we're going to deal with the Docker image that has been downloaded prior from Docker Hub, and we're going to start playing around with it such that we understand how it works and we understand how we can develop with it. Now, what we're going to do is we're just going to talk about the Docker images that exist for Cortex Lab and that you can use for developing with. So if you want to look for Fit Cortex Lab compatible images on the Docker Hub, you should just look for the string CXLB. If you do that, you will see that a number of the images which are compatible that will appear are the ones provided by these three people here. First one is M. Ambert, which is Mathieu Ambert, one of Cortex Lab lead engineers. L. Cardoso, which is myself. And Noto, which is Cyril Morin, the main contributor for the deep learning images, but also one of the maintainers of the Bokeh GUI part of GNU Radio. We also recommend that if you are creating your own images and if you want to share them with the world, you should prepend them with the string CXLB so people can easily trace them afterward. Now we will start with the first interactive session. I just want to highlight that teaching Docker is out of the scope of this tutorial. You can find many good resources for learning Docker out there, and I advise you to do so if you want to use Docker to its full potential. We're going to Docker pull the base image. Well, we already did that in the beginning. We did that before because sometimes it takes a little bit of time to download the first Docker image. And now all of you will have it surely on your computers if you didn't run into any problems. Second is we're going to run the Docker image into a new container on your local computer. Then we're going to connect to a Docker container using an SSH connection with X-Window export. Then we're going to run GNU Radio Companion and we're going to create a Bokeh GUI test. And then we're going to run this Bokeh GUI test and have the Bokeh GUI interface running on the browser. So now we're going to start with our first interactive session. I just want to point out that teaching Docker is out of the scope of this tutorial. If you're interested in understanding more about Docker, you should definitely go on to Docker's Hub documentation for more info. If you want to get the most out of Docker, then I advise you to do so. Well, with respect to the steps that we have to run now, we have these 5 steps. The first step, the Docker pull of the base image, we already did it in the beginning of the tutorial. We can actually verify this by going back to the Docker application, which I'm going to do right now, looking at images and seeing that the image is right here. If the image is not here, then you might have had a problem and you might need to retry the command to have it working properly. Let's switch back to the tab Containers Apps and let's minimize our Docker application. If everything here was correct, then we have finished the first step of our first interactive session. Now let's move on to the second one. So for the second one, we need to run our Docker image into a new container. In order to do so, we will run our docker run command. This will take an image and run it into a container. The line that we're going to use is docker run minus DTI minus P. This will specify the port that is going to be exposed from the Docker to the outside machine. We're going to use the port 2222. That has to be written in this way right here. We're going to give the Docker container a name. Let's call it Cortex Lab tutorial, like this. I have misplaced here my quote, a double quote. And then I am going to give the name of my Docker image. It's going to be Cardoso / CXLB GNU Radio 3.8:1.1. When we press enter, we will have a number which is going to appear, a code which is going to appear on the screen. This is the unique code for a Docker container. Now that we have properly run the image into the new container, we can cross out step number 2, and we can go to the next step, which is step 3, connect to the Docker container via an SSH with X-Window export. So before that, what we need to do is we need to run our X server. In Linux, probably you are already running an X server if you're running Ubuntu Linux or Debian. If you're not, then this will run automatically. So there isn't going to be any problem. In macOS, the default X Window system is the X Quartz. We can run it like this. And in Windows, it is going to be like I advise you to install in the mail I sent to you in the beginning, the VC X server. So you have to run that if you are in Windows. So now that we have run our X window, we can give access for the container to export Windows to the host. We'll do that by doing X host plus. Now we can use the SSH command to connect to the container. We will type SSH minus big Y, which will enable the X window export, minus P 2222, which was the port specified in the beginning, and then the user and the host that we're going to access, which is the container. When we press enter, we have a connection to the container. We will notice that we're running a Debian distribution, and that the machine number are the first 12 digits of the unique ID of the container. In order to verify that our X window export is working, we have to type echo $display, and we should have the same thing, the name of the machine, :10.0. That means that the display environment inside of the container is correctly set. Now we can go back to the slides and we can cross off step number 3. Now we have to go to step number 4, which is run GNU Radio Companion and create a BOKU Gui test. So we're going to do that right now. We're going to go back to the terminal and we're going to type GNU Radio Companion like this. It's going to run and we will have a window which is going to appear like this one here, which is a regular GNU Radio Companion window. Remember that this GNU Radio Companion here is running inside of the Docker container and we are having its screen exported from the Docker container to the actual machine. What we will want to do is we want to create something very simple. We will want to put a waveform generator, a noise source like this. We're going to also put a signal source like this one here. We're going to add them up. So we're going to look for math operators, add, connect the output of this one to the input of this one and so on. For the second one, we're going to reduce the amplitude of the noise by a factor of 100. This. And we will connect now, since we're in software only, a throttle block like this. And finally, I'm going to go to BOKU Gui here in the beginning, and I'm going to look for a BOKU Gui time sync like this. See that even though I've connected everything, the BOKU Gui time sync is still red. So usually what we need to do is we need to specify where we're going to do the placement. This is not done automatically. So we're going to type 0, 0, 1, 1 like this. Now we need to change the options such that we're not in Qt GUI anymore. We're in Bokeh GUI like this. And we can save our GNU Radio Companion file. Let's call it test Bokeh like this. So finally we have finished step 4, so we can cross it out. So now let's go to step 5, where we can actually run the BOKU Gui test application. And now we're going to run this. This window is going to appear. You can safely ignore it. Now we can check if the BOKU Gui server is running by scrolling a little bit up here and checking this line. So this line is saying that your BOKU Gui server is running, so the BOKU app is running at localhost port 5006/BOKU Gui. The problem is that there is no way of connecting to this port from the outside machine to the container. So what we have to do is we have to create a port forward from the container to the host machine. So how are we're going to do that? Well, we're going to stop everything, close GNU Radio Companion, and then exit the container, exit the SSH command that we use to connect to the container. I'm going to clear the screen so everything is clearer. And now I'm going to type a new SSH command, which is going to look a lot like the last one, with a difference. And the difference being that now I'm going to use a new option, which is the -big L, local host, 5006, local host, 5006. So what this new thing is doing, this -L option, is that it's forwarding the port 5006 from the Docker, is the local host, to the outside machine, which is also the local host. So now we have created a bridge for port 5006 from the Docker to the host machine. We can run it, connect it back to our container. Now we can rerun GNU Radio Companion. We can run our BOKU Gui test. Sometimes there is an error, like now. We're going to try it again. Now we have the Bokeh GUI application running at 5006/Bokeh GUI. So what we're going to do is we're going to open up our Firefox browser and we're going to try to connect to the application. So how do we do that? We're going to type http://localhost. Remember that we're locally on localhost port 5006. And then the application is at Bokeh GUI Bokeh. Notice that Firefox is already suggesting to me, because I have already done this before, session ID equal to test_Bokeh. Firefox is trying to connect to the application. And when it connects, we have our time sync here showing the sinusoidal wave that we have put into the Bokeh time sync. Now let's try something a little bit different. I'm going to minimize my Firefox and I'm going to go back here to my testbokeh.grc, stop it, and now I am going to go on to the Bokeh GUI. Now I'm going to go to the Bokeh GUI widgets and I'm going to get a slider. I'm going to put here somewhere on the canvas. I am going to double click the slider and I'm going to call it noise level. Noise level. I'm going to say that it is a float starting at 0.0001, ending at 1, step 001, default value 0. Dot 0001. Going to click on OK. And now I need to change my placement for the Bokeh GUI output. So I'm going to put that at 1011, like this. I'm next going to go on to my noise source, change my amplitude with the variable that we have created, noise level. Now I can save and I can start my Bokeh GUI application. Like this. Now if I go back to my Firefox browser and I go back to the link, like this, we will notice something slightly different. Now I have a slider that I can choose, that I can use to increase the noise of the signal like we're seeing here. see that I can interact with a running BOKU Gui application through a completely web-based control. Finally, we have finished all 5 steps. We can cross this one out, and we're ready to go to the next part of the presentation. Now, it's up to you to try out these steps on your own. We will give you some time to try out each one of these steps. The first one has already been done, and then test on your own to see if you can do all of these steps. We will then continue the presentation. Okay, now let's get back to the presentation. Okay, now that we have tested Bokeh GUI and Docker in a local computer, we want to generate the tests that we want to run within Cortex Lab. So in this second interactive session, we will do exactly that. The first thing we're going to do is we're going to open rxofdm.grc and save it to the roots folder. So let's go back here to our GNU Radio Companion interface. So we're going to click on Open, and now we're going to navigate to the place where the rxofdm is. So we can go to the roots of our container. We can double click on Cortex Lab, Toolchains, Current, Share, GNU Radio, examples digital OFDM. Here we have three .grc files, one of them being the RX OFDM that we're looking for. So we're going to click on it and we're going to open. You will see that it opens a very complicated flow graph here with lots of blocks in our GNU Radio Companion. Before we start modifying it, let's save it locally such that we don't modify the original version. We're going to go to File, Save As, go back to the root of the Docker and then click on /root, which is our home folder. And then if you want to keep the same name, you can keep the same name. I suggest you keep it. Click on Save, which will save it locally. You should have now rxofdm.grc/root in the title bar of our window. So now we have finished our first step here. We can go on to the second step, which is to perform the modifications that we need in order to replace the parts that we don't need by an UHD source. Let's go back here to our GNU Radio Companion. And well, the parts that we need to take out will be these blocks right here that will not be needed. These blocks are actually simulating a OFDM transmitter and are not necessary for us. So what we're going to do is we're going to select all of them like this. When they're all selected, we can delete them like this. Now we can go to the right-hand toolbar, find the category UHD, and then get a UHD source that we're going to place on the canvas. We can now connect the UHD source to the Schmidl-Cox and to the delay ports blocks right here. So we need to do a couple of things for the UHD source to be connected to the right frequency. First thing we're going to do is we're going to double click it, go to RF options, and set our center frequency to 2.49 gigahertz. So e to the power of 9, like this. We're going to click on OK. Our center frequency is correctly set. We will need to change the sample rate variable, which is currently 10 kilohertz, to 1 megahertz, so 1 6 zeros, like this. And now we have finished step number 2. Step number 3 right now is change the main options such that the flow graph uses Bokeh GUI. So to do that, we have to go back to our GNU Radio Companion, double click options, change no GUI to BOKU GUI, like that. Let's save everything. Now we need to add the BOKU GUI elements that will help us debugging in real time this flow graph in GNU Radio and in Cortex Lab. We'll go back to GNU Radio Companion. We will make some space here and we're going to go to Bokeh GUI. We're going to add a frequency sync. We're going to connect it straight to the USRP source. We're going to double click it and change the placement to 1011. And we're going to add a Bokeh GUI slider such that we can play around with the gain of the USRP source. So I'm going to call this Rx gain, which is a variable starting at 0, ending at 40. And we're going to call the default value 10. I need to go back to the USRP source, RF options, and change the gain value to the variable we have just created, Rx gain. We have hence finished step number 4. And now we need step number 5, which is save and generate the Python code. So we can go back to the GNU Radio Companion, save, and then we can click on this button right here, which is generate the flow graph, and this will generate a Python file which will be executed, and we will generate this flow graph. When we press it, there is a small message here saying generating root rxofdm.py, meaning that we have correctly created our receiver flow graph in Python. Now it's time for you to do it on your own. Here you have the steps and you have the information which is needed in order for you to make this flow graph work. When you finish doing it, we will be able to go to the next step. Okay, now let's get back to the presentation. Now we're going to start our third interactive session. In this section, we will prepare our image to use it in Fit Cortex Lab. These are the steps that we need in order to prepare our image. We will do them one by one right now. The first step is to do a Docker commit. So go back to our GNU Radio Companion. We're going to close it. We don't need it anymore. And then we can go back to the right-hand side terminal that we will use to interact with Docker. In order for us to start, we first need to see the process of our Docker. So we have to do a Docker PS. Docker PS will give us a message that comes out where there is a container ID, there is the image, the command that was used to start it, when it was created, the status, and other information. What is needed for us is mainly the container ID. So for anyone who has ever used a version management system like Git or SVN, this will seem like something very well known. When we do the Docker commit, we need to specify a message, for example, -m, and then let's say preparation for fit/Cortex Lab. We need to give it a container ID, which is exactly this same number right here. I'm going to copy and paste it like this. And then I'm going to give a repository and a tag. So the repository will be your own. You're going to put here your own Docker username. Mine is L Cardoso / and now I'm going to create a new repository. So I'm going to call it CXLB Docker tutorial :1.0, which is the tag version here. So I've now committed. So I've now committed my changes to this new Docker image. Now we have to do the Docker tag. The Docker tag will prepare the image before we can push it onto the Docker registry. So let's go back to our terminal. We'll have to do a Docker tag, and then we'll have to put here the name of our image that we have just created. Like this. And then the version that is going to be sent to the server, which is essentially the same thing. Like this. Finally, we have to do the Docker push, which will actually upload the Docker image to the server. So we're going to do it like this. Docker push. L Cardoso / CXLB Docker tutorial 1.0, and when we press enter, it will send everything onto the server, and this should take a little bit of time. When all of this is finished, we can actually verify that the Docker image is present in the Docker Hub. So mine is finished. You can go back here. We see that the command has finished running. So now I can go to the Docker Hub like this. The window smaller so see. So now my Cortex Lab Docker tutorial appears here in my list of repositories. You should see the same thing on your side. Now it's your turn to do these steps. You have here the list of steps. When you're finished, we will continue with the presentation. Okay, now let's get back to the presentation. Now that you have all finished, let's state some conclusions. So what I have shown here is the easy way to prepare a Docker image for Fit Cortex Lab. This is not the right way to do it, or the right way which is suggested by Docker. The problem with this is that it does not support minus automation because there's no command started in the end. So the proper way to construct your Docker image is creating a Docker file, which will look like the one appearing here on the screen. You have from El Cardoso CXLB / GNU Radio 3.8 colon 1.1, and then you will add some commands which will do the necessary steps for you. Here I am running a git clone command where this git clone will fetch the information from a git repository, for example an OFDM receiver, and then I will copy this OFDM receiver to the root folder where I can run it from afterward. Now let's go to step 3 of this tutorial, which is connecting to Fit Cortex Lab. But first, let's review the Fit Cortex Lab experimental tools. We have talked briefly about OAR and minus, but let's look at how they actually work. So for Testbed reservation, we have the OAR suite of tools. They will allow you to do reservations, which can carry many experiments inside. A reservation can be either exclusive, meaning that you have the full power to control the testbed, or it can be shared, in which you can share a reservation time with other users. Every reservation will carry an identification number, and you have two main commands. They're not the only commands, but two main commands which are used here. OAR sub submits a reservation that can be either immediate, meaning it's interactive, so you have to check if the testbed is free, or it will give you the next free slot. Or it can be a future reservation, meaning that you can reserve for a certain moment that you know you want to work on Cortex Lab and you don't want anyone to take it from you. Then there's OAR del, which will delete a reservation. So if you have created a future reservation, you can delete it with OAR del. Experiments that exceed the reservation time will be automatically cut short. And in order for you to check if the testbed is free, there is a tool called drawgaunt, which allows you to visualize all the reservations. Drawgaunt looks like this. It will open in your browser, and it will give you an interface where you can skim through time and look at free slots. For example, here we have these colored bars, the orange, the purple, and the green, which are reservations for all the nodes inside of the platform. These three reservations are going back to back, and there's no free time in between them. Wherever the drawgaunt shows a white place, that means that the testbed is free. You have here the link to access the drawgaunt interface and check for reservation time. Now we talk about the minus tool, which is an experiment management tool. So the minus tool will allow you to create your experiments, to submit your experiments to the nodes, and it will take care of all automatic parts of starting, controlling, and stopping an experiment. So one experiment contains code, which is going to be executed, libraries, and a scenario description. In our case, if we're using Docker, then it's only going to contain a scenario description because the code is already inside of the Docker image. We're going to be able to convert a folder with all of this information into a task file, and then we will be able to submit the task file to the experiment control system. A task, like a reservation, can also be identified by an ID number. Inside of your reservation, tasks are executed first in, first served. So in the order that they are submitted. Tasks can be stopped at any moment, can be interrupted, can be aborted. Minus also provides a way to list all of the running and waiting tasks and give access to the logs and debug for each one of the nodes and for the experiment control system. To better understand how the task works and how the reservation works, let's see what is a reservation versus an experiment. A reservation is a slot of time, like this, here in gray, in which I can add tasks. So the tasks here are shown in red. Tasks must live inside of the reservation. Outside of the reservation, you cannot submit tasks. So you can submit one task, but you can submit several other tasks. And every task will receive its own ID number. Each task will carry one experimentation, which is going to live inside of a reservation. Now there are some things to point out here. When we're using the Docker system, the reservation starts a few minutes after it has been successfully accepted. So when you reserve the testbed, there's a slight delay in between the time that there is a successful reservation and the time where you can actually start submitting tasks. If you submit a task and if it doesn't run, it probably means that you have to wait a little bit more in order for you to send a task again and have it be accepted by the experiment system. When the task is submitted for the first time, there's a significant delay for the Docker image to be downloaded. So you have to be patient while that happens. You probably want to create a reservation which is much larger than the time necessary to download the Docker image, especially when it's the first time you download the Docker image. Once the Docker image is downloaded, it is stored in cache, and the subsequent tasks which will be submitted with the same Docker image will run straight away. When the task is running on the nodes, it is only then you can SSH to the node. In order for you to be sure that your task is running, you will have to use minus to be sure that the task is in the running state. For our tutorial, we will need an SSH bridge to access the nodes directly from home. And we will also use an SSH port forwarding to allow the X window export, but also the BOKU Gui ports to be exported to your local machine in order for you to access the BOKU Gui interface. So for the remainder of the tutorial, we're going to use these nodes for the student numbers. In the mail that I sent to you, you have received a number. This number is going to allow you to use one of the nodes inside of Cortex Lab. If you're student number 1, for example, you will use node 6. And the address for node 6 is mnode6, everything together. So depending on the number that you have been assigned, you will use a certain node with the address which is given in this table. So this is the moment to write down your node and the address that has been given to you with the student number that has been issued in the email address. And now we can go to our fourth interactive session. What we want to do is we want to connect to Airlock, which is the front server, create the task folder, create the scenario, and then create the task file. And then we want to reserve the testbed, write down the ID, and check if the reservation has been correctly done. Since we're many students, I have already created a container reservation. And inside of the container reservation, you are going to create your own reservations. Each reservation that you're going to create is going to concern your node. So now let's get started with the steps for the fourth interactive session. The first thing we're going to do is we're going to connect using SSH to Airlock. Let's switch to our terminal screen where we see now a different configuration of terminals. To the left, we have two terminals which are going to be used to connect as a user to the nodes. And to the right, I have a terminal which I'm going to use to connect to the SSH Airlock. So we're going to use the terminal to the right to connect to the SSH. In order to do so, we need to use an SSH command, SSH -y. And then we're going to use our username, in my case is Cardoso at gw.cortexlab.fr. If your identity file is not the same as ID RSA, which is my case, then you need to specify the path like this. Hopefully in your case this is not necessary and you can just go with the first version of the command I've just shown. I'm typing my passphrase and now I'm connecting to Cortex Lab. So finally we are at Cortex Lab. And we can go back to the slides and cross the first step. Now we need to create a task folder, create a scenario file, and create the task. For that, we're going to go back to our terminal, and we're going to first cd to the folder tasks, which might exist already in your home folder. I am going to create right now a new task folder. So I'm going to create mkdir, and I'm going to call it Cortex Lab tutorial, like this. Then we're going to have to create a scenario file. For this, we're going to use the command pico, which is an editor, and we're going to create a file inside of Cortex Lab tuto, which is called scenario.yaml. So I did a mistake. It's Cortex. So the scenario YAML, this is the file which will specify the scenario that is going to be run in Cortex Lab. So each task has its own scenario, and the scenario allows us to say what are the things we want to run on each of the nodes. In this case, what we want to do is we want to specify some basic configuration parameters here for our scenario. So we need to start with a description. And we're going to call this OFDM RX Cortex Lab tutorial. We need to specify a duration for which this task is going to run. This duration has to be a multiple of seconds. So let's specify that we want it to run for 10 minutes. So we're going to put a duration of 600 seconds, which is 10 minutes. Now we need to specify the nodes and what each node is doing. So in this case, we're going to have to create a node section, which is like this. Nodes. And then we will indent for each one of the nodes. So for example, if the node I have chosen to work on is node 32, or 34, sorry, I'm going to write it like this. Indent again. So we're going to use the keyword container to specify the details of this container. And then we're going to use the keyword image to give the image of the container. This is going to be El Cardoso / CXLB Docker tutorial with tag 1.0. And we're going to give the command, which is a command that has to be run /user /sbin /sshd -p 2222 -d to start the daemon. And now everything is ready. I can Ctrl X and save to the scenario YAML. Now that everything is done, we can create the task. So we're going to do that by typing -task create Cortex Lab tuto. And the task will be created like this. We can go back to the slides, cross off the second step. Let's go back to the terminal. And now we're going to use OAR sub to create our reservation. In this case, I'm going to type this command. It's a very complicated command. If you type it the way I'm typing right now, it should work. So OAR sub minus T. This is the container reservation that I have created prior. So the container reservation number is going to be 3250. So inner equals 3250. Well, in my case here, I am doing this inside of another container, so I'm going to substitute 3250 by 3251. But at the moment that you'll be running this, you should be running with 3250 and not 3251. Now, option minus L, and then in between curly brackets, I'm going to specify the network address of the nodes that we want. So this is a small piece of code that looks like this. This is going to be m node, and then I have reserved the node 34, so 34 dot CorteXlab dot fr, like this, close parenthesis, close double quotes, close curly brackets, slash node equal to 1 because we only have one node, comma, wall time, and this is the total time for which my reservation is going to be valid, 0, 30, 0, 0. So I want it to be valid for 30 minutes. And then minus I, meaning that I wanted to use an interactive mode. We're going to press enter, and my reservation is being done. I already have a reservation ID, which is 3257. Could write that down somewhere. And now we have a prompt saying that everything has worked correctly. Now we can go back to our screen here. Now we can go back to our slides and cross the last option. So now that we have done all these steps, it's up to you to do it on your own. So here are the list of steps that you have to do, and I have put here inside of this blue box a reminder of the commands that you have to run on your side. As soon as you are done, we can continue with the presentation. Okay, now let's get back to the presentation. Now we're going to go to part 4 of this presentation, which is launching the experiment itself. So here are the steps of the 5th interactive session. So the first thing we're going to do is we're going to submit the task and verify its status. Then we're going to SSH to the node, launch the OFDM receiver, check if it's running correctly. Then we're going to open a browser locally in our computers, and we're going to connect to the BOKU Gui interface, which is running in one of the nodes. Then we're going to play around with the gain such that the receiver correctly receives packets. So let's start with the first thing, which is submit the task. So now let's switch to the terminal. So we have a reservation right now. We need to submit the task. So I'm going to stay here and I'm going to type -task submit, and then the name of my newly created task, which is CorteXlab tuto.task. So the task has been submitted, and we have the task ID, which is 18,139. If we want to check if the task has been correctly submitted, then we need to do a -testbed status. So it says that the total number of tasks that have been run until now are 18,139, so ours is the latest. The number of tasks waiting are 0, and the number of tasks running are 1. And there is a task with ID 18,139, which is running right now. If we want to check if this is running correctly, then what we can do is we can just do a -log. -log will tell us everything that is happening right now in Cortex Lab. So right now we see that the pool has been complete on node 34, sorry. And our task is still being deployed. We can now go back to our slides and cross off the first step. Now we have to go to the second step. So for the second step, we need to be sure that Minus has completely started the container at the node. So you see that after all the pool complete messages, it has now some new messages saying that the Docker is being started with this container number, and it is running and waiting for it to end. So now we can go to one of our other terminals. I'm going to choose the bottom one, the green one, and I'm going to try to connect to the node. So in order to connect, we're going to use the SSH command, which is going to be shown here. -J, which identifies the jump command. So we're going to jump to the node directly. We're going to jump through the server, which is the gateway. And we're going to jump to the node that we're using. So I'm going to put here root at mnode 34, because this is the node I'm using. You will substitute node 34 for the node that you're using. -p 2222, this is the port. And -l will do the port forwarding from the container to the outer machine. This is going to be localhost 5006, localhost 5006, like this. So if you press enter here, it should work for you. But for me, I have a different configuration, so I have to change this part here. But the current command will work for you. Typing my passphrase, and I'm in. So right now I'm connected to root at mnode 34. And I can go back to my slides and cross off the second. So now we have to launch our OFDM receiver. In that case, I'm going back to the screen, and I'm listing here. My OFDM receiver is there, as we would expect, right here. So I'm going to run it by writing /rx ofdm.py. This is going to start my receiver. And as the receiver started, I already have some debug info right here running. So now it is running. We can go back to the slides and cross off the third step. Now we need to open the browser and connect to the BOKU Gui interface. So now we go back to our terminal and let's launch Firefox and let's connect it to our receiver. This is going to be HTTP one. So this is going to be localhost 5006 BOKU Gui. Everything is the same. Just changing this for RX OFDM. Loading. There we go. We have RX OFDM working here. Now we can go back to the slides and we can cross off step number 4, and let's go to step number 5, which is to fix the gain such that the receiver receives packets correctly. So in this case, it is already receiving. We can see that the OFDM spectrum here is looking good. And we can see, if we switch back to the terminal, that we have a proper packet number value here, which is being identified here in this part. So this means that we're receiving correctly. If we weren't, then we would have to change here the value of the gain such that we receive the signal correctly. Either raising it if you're too far away or decreasing it if you're too close. Now, it is up to you to take the steps yourself. So here are the steps that you have to accomplish, and down below you will find the actual SSH line you need to use to connect to the node. After you're done with this, then we can continue the presentation. Okay, now let's get back to the presentation. Okay, so now we have finally finished this tutorial. Now you know how to deal with a Docker locally on your machine, create an image that you can export to Cortex Lab, bring it to Cortex Lab and run it on Cortex Lab with full control from your computer. Now you have all it takes to use Cortex Lab on your own, and you can use it to learn GNU Radio, to experiment, to test out new systems, new physical layers, whatever you want to do. If you have a specific need in mind, do not hesitate to contact us. We're always open to taking suggestions. You should check on our website and Twitter to be informed of the evolution of the testbed, and both of those links are down below. And in the website, in the wiki.cortexlab.fr, you will find more tutorials, tips, and examples of usage. And with this, we finish our tutorial on using Cortex Lab with GNU Radio and with Docker. I hope that this tutorial has been useful in learning how to use Docker with GNU Radio and learning and understanding how you can use Cortex Lab to do your own experiments, learn GNU Radio, get crazy and try out new things. I'm now ready to take any questions, and thank you for your attention.